Well, I think we can get started. Welcome back, folks. We're on to week 12 of the 16-week semester. So at the end of this week, you can congratulate yourself for being 75% done. Excuse me. For as far as the announcements goes, we have quiz 8 that's due this. Oh, I said Wednesday. That should have said, sorry about that. Our quizzes are due on Thursdays. Just put in a quick revision, why not? So quiz 8 will be due on Thursday, and our ninth quiz is going to be based off section 13.3. So that one will be extremely helpful for the upcoming third exam. Quiz number 8, I believe that one was based on the probability section, chapter 12. So this one was kind of a faster kind of problem, I'd say. Other questions so far? Okay, well, for the other announcements, once we finish section 13.3, probably on, I'd say, Wednesday, we're going to begin working through chapter 14. Like a lot of these chapters, these take a few days to get through, so this one will be probably finished after the exam. And because we have an upcoming exam, it's going to be on the 11th, a week away from today. That means our Thursday's class, November 7th, that's going to be another one of our review kind of days, a student-directed review set. It'll be the entire day if we want it to be, or just as many questions until we run out, and then we'll go back to chapter 14 if necessary.
What chapters are you testing through?
Great question. I'm glad you asked about that. And I was also really behind on doing this weekend. Sorry about that, folks. I usually try to get this done like Saturday, probably. This happened on Sunday. So the official setup is going to be chapter 7. That one's on linear regression, so expect just one kind of problem. Take a look at your quizzes, the old lecture notes to see about what it should look like. Chapter 10, this one's based off determining if you have an experiment or an observational study. Also questions about statistics versus parameters. There could be 1 or 2 questions from that section, but they're really fast and short questions. Chapter 12 is our probability section. I'm only going to ask exactly 1 question. If you look at the notes in chapter 12, we indicate as a hint on the ones that would make suitable exam choices. And like usual, quiz number 8 is a great example of what would make a good exam question. Then finally, in chapter 13, what we're doing is one of these, a confidence interval procedure from start to finish. Will look very more similar like example 1, where there's a part for the parameter, a part for the statistic p-hat, a part for the standard error, and so on. I'm not going to ask any of the weird concept questions like we're going to see on example 2. So this kind of stuff won't make it to exam 3, since we're only looking into it this week. So as far as chapter 13 goes, the major purpose of chapter 13 was to do basically this. That means 13.1 and 13.2, that was us just inching along so we could do the full procedure and show how it all logically comes together. As far as 13.3 goes on the exam, it'll once again be just the full confidence interval procedure, not the ancillary questions around 13.1, 13.2. So that will be our exam. It'll be about 5 questions as normal. And same exact stuff on the exam. Same comments as well. Don't forget to do your review sheet, or excuse me, notes early. Before you even study for the exam is a good time to put them together. And just like at the other exams, it will require a T94 calculator. I'm going to need to indent that. I don't know why it's bothering me, but I'll come back to that. Any questions at the moment, folks? Okay, and this is the usual stuff. Version 1 of the sample exam is brand new problems, or supposedly. Let me know if something is not quite right there. These all have solutions at the very bottom. And the things I try to do to be really careful in these notes is, if X bar came up, I try to put in a Y bar instead. Some of them might have sneaked past me. Another one was, I say parameter instead of population characteristic. In the old book, it was population characteristic. So I try to eliminate those as well. But if you see stuff that's weird language like that, let me know and I'll try to get it corrected right away. So that's our...
You said parameter characteristic is population?
Population characteristic is synonymous to parameter. We said that a couple spot in the notes, but we almost exclusively say parameter, so that's way easy to forget, I think. Version 2, this is just as good as version 1. The problems are more familiar. All I've done is went on a section by section basis, pared it down to just the problems, taking out all the notes. So now it's basically just one gigantic worksheet. I also deleted some questions I didn't feel like would fit into an exam setting. So that's why the chapter 12 notes as a worksheet format only has example 4 and example 5 and example 6. As a hint, these are the type of questions you should expect on a real exam. So that's what we'll be doing coming up on Thursday, reviewing for our third exam. But any questions at the moment, folks, with any of those course materials? Okay, well, with where we're at so far, we're most of the way through section 13.3. We have a couple problems that we want to go through, and then we'll get into chapter 14. Essentially, the idea is in chapter 13, we have categorical data with two outcomes, success versus failure. But once we go to chapter 14, we have one quantitative variable that we're going to be looking into. And that actually makes a lot of big changes. You'll notice a whole bunch of weird materials here that we'll take a look at. But before we get started on that chapter 14 stuff, here's where we left off right about here. Again, these are the very common exam 3 type questions. You could expect these kinds of questions as well in the final exam. And the format of these questions are always pretty similar. I think the only odd one out is example 2 with the concept questions below. This is mainly to help with some of the concept questions that you're going to see in the actual homework. Get this put away here. So the way this problem started, it's familiar data. We've seen it before. We said P is going to be the true proportion of all infants that have an adverse reaction to this whooping cough vaccine. We said to the vaccine. That's still great. It captures the context. If you say vaccine in this situation, you've got to be referring to the whooping cough one, since we're kind of constrained in that context. So the success here is having a reaction. Sample size was at 339. And we didn't have the number of successes. We just had the statistic, P hat. Well, any questions, folks, with our rundown with what we ended on? Okay, as far as the conditions go, if it's asking for the conditions of the large sample confidence interval, we're really just checking two things. First thing we're looking into is if we have a simple random sample. I'm starting to realize this feels kind of redundant. We kind of looked into the same sort of thing earlier in section, I think, 13.1 or 13.2. But let's re-say it again here, just so we're not skipping the whole part. So reading through here, no information tells us this was a random sample. So say on condition 1, it's unknown. If the n equals 339 infants was randomly selected. So we have no clue about their sampling design. They could have been a very bad non-representative sample. We're just going to have to trust them on that one. Condition 2 is just determining if our sample size is large enough. We have to have at least 10 successes, at least 10 failures. So here we'll go and calculate. Number of successes is equal to this formula. We go sample size n, multiply it by the statistic p hat. So this will calculate our successes. Using the information over here, it's going to be 339 multiplied by 0.2035. So this is our first calculator computation. 339 times 0.2035. So we've got, if we round to the nearest integer, good call, these are infants, so we don't have fractional amount of them. We'll call this 69. It has to be greater than or equal to 10. Let me highlight that portion since that's the benchmark we have to pass. So we're good on this end. Just put a little check there just to emphasize that. Finally, number of failures. is equal to, different ways to calculate this are, if you know the number of successes and you know your sample size, you can just simply go n minus 69. So 339 minus 69. I think that comes out to 270 altogether. That's also definitely greater than or equal to 10. So another check there. And we can say this shows the sample size is large enough. So what we know about the problem is we know the sample size is large enough so that our confidence interval will be accurate once calculated. We just don't know if the sample was representative in the first place. We want them to be randomly selected, but until we hear that information, we are not completely certain if that's met. So if this feels kind of uncomfortable to you, I kind of understand. That's where the next statement might come in handy. You might say, the conditions are met. Provided these data came from a random sample. We prefer the simple random sample method, but any random sample is good enough or better than nothing. So that's the conditions in the problem. Next, part C is asking us to get right to the meat of the question, just construct that 99% confidence interval. Any questions at all before we jump into that phase? Okay, let me just grab a couple quick screenshots. We'll need that right there for this next portion. Okay, so we have our information here. Maybe the first thing we should do is take a look at the confidence. If we're at 99% confidence, we can take that information and give a value for Z star. So maybe give this a specific color just to make it pop out a little bit more. Let's go with, how about purple or whatever that color is. Z star, the critical number at 99% confidence, we could calculate it pretty quickly, but this is something that would be a really strong addition to your exam 3 notes. Look up the confidence level, put this on your notes. This is on the second page of the same document, and just use 2.58. So this is something that's pre-calculated. On a real exam, it will always go this way. Down below, sorry, go ahead.
Is that gonna be on the test, or are we gonna?
This right here?
Well, it is like 90%, is it always 1.645?
Yes, for this particular procedure,
Okay.
yeah. So if you put this on your notes for the exam, these will always be the right values here. I'm really glad you asked that because something not so great happens. In chapter 14, they have to be recalculated essentially on every single new problem. So that's awful. But for categorical data, these are fixed values. So from this table, we grab the 2.58 to match up the 99% confidence. Does that make sense to folks on why we're using 2.58? Okay, let's drop this down. Back to where we were. At 99% confidence, Z star is 2.58. Let me know if I misremembered that. That sounds pretty accurate. This has been rounded to 2 decimal places. Now let's see, what else do we need? We have p hat already. We just stated that at the start of the problem. So next thing we're going to want is the standard error of p hat. So let's write that out. SE of p hat, to stand for standard error of p hat, goes, first let's imagine this is an exam question. If you've run out of time or if you're just not sure, writing this down, p hat, 1 minus p hat divided by sample size n, I would consider this already partial credit. You knew that this is what the standard error looks like, so that gives you good credit there. You get most of the partial credit by doing this. Plug in p hat at 0.2035. 1 minus the same figure, 0.2035. divide by the sample size n, which is at 339. And if you show this on paper, again, this is major partial credit. Any mistake you make in your calculator, maybe you lose a half a point, nothing major. But let's try to get it accurate from here with what we've got. So I'll go with the put it in one line method. Go second power 2 button like that. 0.2035, 1 minus 0.2035. We'll close the parenthesis, hit division by 339. And let me know if you're getting something different. For me, the standard error is 0.02186. Our problem, we want to round to 3 decimal places, but this is referring to the very final answer because that's like an intermittent computation. Let's round this one to 4 decimal places just to get extra accuracy. So it'd be 0.21, 0.21,
0.02.
thank you, 0.0219. I think that's what my brain was struggling with on that one. 0.0219. Does that look all right to folks so far with standard error? Okay, so if we're going to build out any confidence interval, these are the things that we want. Right, we're adding just an extra decimal to this one, just so that when we go to our very final answer, we have that extra accuracy. So this one has a computation in the middle, we're getting just a little bit, giving just a little bit more accuracy. And same with this one to 4 decimal places as well. But other questions at the moment? Okay, if you like doing this as a sequence of steps, this is not a bad way to think about it. Step 1, state your critical number. Step 2, come up with your standard error. And a really good step 3 is just write down on paper the entire formula for the confidence interval. It's going to be p hat plus or minus z star times standard error of p hat. And let me see if I can fix that color coding real quick. So once we get to here, this is a great thing to write down as you're studying or practicing problems in WebAssign. Just makes your mind more familiar with what the formula is, how to work with it. And if you write that down like 10 times studying for exam 3, you'll remember it and you won't even potentially need your notes. So first, in place of p hat, substitute in the value 0.2035 down the next bottom of the notes. Then it goes plus or minus. In place of this z star, use the 2.58 value in the table looked up. And then finally, in place of standard error p hat, we're plugging in 0.0219. So we're just about there. In our step 4, we're going to give the entire answer for the whole confidence interval. Looks like we can delete that screenshot now. Any questions or comments, folks, to this stage? Okay, let me grab a really fast screenshot one more time while we're mulling over where we're at so far. Because we're giving a confidence interval per parameter, the unknown parameter, it's good to keep this in the back of your mind as you go to build this out. In MyStats Lab, you're just having 2 boxes where you put in the smaller value and then the upper value, the larger one. But on paper, it's not a bad idea to go like this. Again, it's basically just a huge reminder of what you've calculated. P, the thing we described at the very beginning of the problem, is now in the middle. It goes between 2 different values. So in the calculator, the lower value that goes here is formed by using the minus. So let's write this whole thing down, but with a minus in the calculator first. So it's going to be 0.2035 with a minus, then 2.58. Using parentheses to indicate multiplication, basically just writing it down verbatim as we see it on the page. 0.0219. And that's going to be our lower end of the confidence interval. At this stage, we're done with the problem, so we're really going to round it to 3 decimal places this time. So to 3 places, it's a 0.147. Sorry, say again? 0.2. I bet you it's probably the last four numbers here. That's how I was reading it out when I was trying to give the answer. I forgot there's zero there.
Oh.
Oh, that would give me something totally
0.02.
different.
19. I think yours is wrong.
Point.
0.0219.
Oh, it had to have been that last one that would have messed it up. Thanks for spotting that. 0.0219. Delete there. Thanks for the assistance on this one. I bet what I did is I switched the 1 and the 9 or something. Yeah, that's all it takes to lose the whole problem. That's why putting it down on paper is massive. Switch the wrong 2 digits and there's no way I can tell how close you really were with your answer on paper. But if this is totally messed up, that's okay. I'll look at what you put down right here, award partial credit based on it. So the better value is 1.147. More accurate this time, but same value. Strange. Let me type it in again. So if we make a couple mistakes like this and it's still not coming out right, here's the next best strategy. Just wipe everything out, start fresh. That's sometimes the best way to go. So let me try it in again as well. 0.2035. Then a minus and 2.58. Well, you don't necessarily have to. That's more of a stylistic choice. So let me do it this way without. 2.58. Parentheses are because that's how I write on paper, and I usually just type it in verbatim. But you can just totally hit times, and it works as well. 0.0219.
Oh, see, now I got one. Maybe I had something messed up.
And now I have a 0.147. Sometimes that's how it goes, and I wouldn't worry about the old error. It's just gone in the ether now. Sometimes if you make a repeated mistakes, like imagine it's on scratch paper, just throw it out and start over fresh. It's hard to find a tiny mistake. It's easy to just do it right the second time, I think. So 0.147 on the lower end. Then our next strategy is use the up arrow to select that and hit enter. If that doesn't work on your calculator, it might be a TI-83. Go like this. Hit second and the enter button. It gives you your last entry. So that's how you can copy paste. Scroll left. And we're doing this upper value the moment you change negative into a positive right here. Oh, I could see that. Yeah. That's a little bit tricky in my stats lab because I think if you give the larger one first as your answer, they might write that as incorrect. They're very, very picky. So with the plus, my larger one is 0.260. Yeah, that must have been what it was. So 0.260 goes here. And now that we formed that confidence interval, we essentially have the practical interpretation. We just need to write out what P is and mention again the level of confidence. Well, any other questions or comments, folks, to this stage? Okay, this whole experience of write down a formula like that, plug in the information, that's the major reason we use the 1.5 IQR rule of thumb. It's practice just doing the same sort of stuff. You write down a formula, Q1 minus 1.5 IQR, substitute a bunch of stuff and get an answer out. So that part of the problem is like the mathy part. But this is the tough part, the practical interpretation. It always wants the context to this. So here's where we go. Remind yourselves what the original parameter was. You'd be looking at the top of the page. But definitely start off by saying the level of confidence. You don't have to make it your first statement. You have to say it at some point, and as long as you say it, you're fine. I find it's good to just lead with that statement. We can say now, with 99% confidence. Now, the moment we said that, we're just going to interpret the statement here by the red dot. We start in the middle and read out what P is. So with 99% confidence, the true proportion, let me control Z that for a moment. There's nothing wrong with a proportion, but the better interpretation is when we turn these into percents. So I'll say their true percentage. of all infants that have an adverse reaction to this vaccine. Now we just say is between these two figures. You wouldn't lose points if you went 0.147. In my stats lab, though, watch out for a percent symbol. Then you do have to convert it. But for the purpose of our interpretation, we'll definitely go with the percentage and say 14.7% and 26.0%. So we have found an estimate of the true proportion P. Really, the first estimate was that, 0.2035. But it's not the most honest estimate since there is variability and error in making that estimate. And it's captured here. The low end, it says low is about 15%, just under. On the high end, it's over 25%. So in the worst case, the true proportion of infants that would have a reverse reaction is around 26% of those infants. It might sound bad, but remember, an adverse reaction could have been anything, a crying fit and then they're fine, or maybe something more medical emergency like. We just don't know. But that's one thing that's also kind of interesting about making this estimate. The sample size was large too, 339 infants, very large sample, and yet there's a really big range in making that estimate. And that's pretty typical, but that's where the follow-up questions are going to start coming into play. Any questions first, folks, on coming to this conclusion here? Okay, so we have that percentage. And here's the interesting concept questions, mainly for the purpose of the MyStats Lab homework more than anything. I think these are pretty tricky questions, not the kind of questions I would bring to a real exam. So you can say for an exam 3 question, pretty much it ends at part D. But let's take a look into this. It now asks us in part E. We had a large sample size, 339, it's right here, and we're being asked, if the sample size were to increase, would our confidence interval from 0.147 to 0.260, does it become wider or narrower? Any volunteers for what should happen? Turns out it wouldn't become wider, but I like how you mentioned more information. That's definitely the heart of this problem. So it turns out it does become narrower, and you're absolutely right. The larger the sample, the more information we have. But then why is it making the interval narrower?
What narrower on what? Is there a graph that we need? So on number 4 is the difference between 0.147 and 2.60. It's saying there's a difference between the greater or lesser.
Maybe by narrower, it could turn into something like, say, a 0.18 less P less than maybe 0.22. So this would be a narrower version, and now this one would be wider. So by narrower, we just mean the number's getting closer and closer, the lower end and the upper end. And that's good in a certain sense. The more wide your interval is, the less certain we can actually be in the plausible value of the parameter P. But the narrower it is, the more P is constrained between the upper and lower bound, we have more precise information. So here's what would happen. If the sample size were to increase as n gets larger, the interval becomes, now I claim narrower, but that means I have to explain it. So we'll do it the best we can. Narrower, that's kind of a weird word.
More narrow.
I think that's a better way to say it. Becomes more narrow. So why does it do that? Well, the best way to think about it is just write down the formula for the confidence interval. It's p hat plus or minus z star multiplied by the standard error of p hat. And this question is all about n because we're wondering as the sample size increases. We're just saying n gets larger. Let me convey that better. So n is captured here. That's p hat, number of successes divided by n. But that only affects the center of the interval. It's not going to affect how wide it is. If you want to change how wide it is, you have to change how this number gets affected. But Z star has nothing to do with the sample size. It's completely determined by level of confidence. The only last thing we can take a look at is standard error p hat. So formula for standard error p hat is this. It's the square root of p hat multiplied by 1 minus p hat, or you could say q hat if you prefer, but it looks like we're just throwing in what q hat is. I think that's a better way to think about this formula. It's divided by the sample size n. So let's take a look. So far we've said the width of the interval is controlled by this part. So this controls the interval width. In fact, we gave that thing a name. This is the margin of error, in other words. This is the margin of error. So if we want to make our sample size larger, it means the denominator right here under the standard error is getting bigger and bigger. Let's put a little yellow there to emphasize that. And we've calculated standard error more than once. Let me see if I can call it back. Let's go up arrow until we get something good. There it is. That's us calculating the standard error on this expression. Sample size was 339, and we got a standard error 0.0219. But let's make n larger. Making n larger means just put a bigger number here. Let's say we put in 1,024. 1,024 is a pretty common number whenever we're sampling for categorical data. If it's 1,024, then it does become smaller. It went from 0.02 to 0.01. It's about half as large now. So if you make n bigger in this denominator, standard error gets smaller. Let's say that's right here. As n gets larger, SE of p hat gets smaller, making the interval, let me space that out better, making the interval narrower, more narrow, forgot. So that's how this comes all together. So larger sample sizes are really great because the larger the sample size, the smaller this whole thing circled is going to be, only because you're putting something in the denominator that grows, making standard error smaller and smaller and smaller. But also notice we essentially tripled our sample size and only got cut down by half. That's the trouble with the square root. If you want to really reduce this, sample size has to go up by a lot. But any questions, folks, with our part E? Okay, in a certain sense, this is good. Narrower intervals are what we want. They make our conclusion more precise. And so this is
bigger the sample size, the less margin of error.
Exactly, your margin of error gets smaller. That's a great punchline to this. So this is good in the sense that the larger n is the smaller, let's say it the way you said it, the margin of error is. And now that we have that down, the next concept question is just as tricky, I'd say. But any last questions at all, folks, with part E? No, no worries. I promise not to scroll. Okay, well, for the next one, we did a 99% confidence interval. We think of higher confidence as being better because we have just more confidence that the procedure works. 99% confidence just means that this method, if we repeat it over and over again, has a 99% success rate in actually capturing the true unknown parameter between whatever those two numbers are. So the confidence level is a probability the whole method works in the first place. So that's why this is so awkward. Higher confidence is better. But let's take a look at part F with that statement in mind. Part F is asking, if the confidence level were to decrease down to 95% from 99%, let's see, would that resulting confidence interval become wider or narrower? This one's just as tricky. Any volunteers? It would be narrower. Good call. If we drop our confidence, remember that's a bad thing. Higher confidence is typically what we want. So if we drop our confidence, we are rewarded with a narrower interval, which is something that we do want. That's a little bit awkward in a certain sense. And it's the reason why we always say the level of confidence. That way, that's a kind of transparency. It's a way of being honest when we say what our interval goes from. But we also have to explain why that's true. So that's the hard part. Let's write it all out. So first, we start by just mentioning the confidence interval. It's p hat plus or minus z star times standard error p hat. This time we're not affecting the sample size, so p hat doesn't change, standard error doesn't change. What we're doing is we're decreasing the confidence level. Z star changes. So at, excuse me, 99% confidence, Z star is equal to the 2.58. That's the figure that we cited to finish our last problem to get the confidence interval. So now, if we decrease to 95% confidence, Z star becomes 1.9600, or just a 1.96. So that's interesting because of what it means is this whole thing at lower confidence gets smaller because Z star itself gets smaller. So we can now say this means the margin of error which is referred to as M, which is equal to the Z star times standard error p hat, gets smaller. And so the interval is narrower. Deserves an exclamation mark, I'd say. But does that make sense to folks so far? Okay, again, this is really kind of bad in a way. If you're allowed to just use whatever confidence you would like and not report your confidence level, why not just use 2% confidence? Z star is going to be practically zero, and your confidence interval is going to be extremely narrow, looking like everyone just worked really hard on their statistics. But it's all kind of a lie. There's almost no confidence in your interval at that point. And so that's, again, the major reason why if we drop confidence and we're rewarded by a narrower interval, you have to at least tell people, hey, we're at 90% confidence, however, or 80% confidence. With that kind of transparency, it won't come back to bite us. Well, any other questions or comments, folks, with that concept there? Okay, well, to paraphrase everything, larger sample sizes goes the way we would want it to. It narrows out the interval, and that's what we want. We get a more precise estimate in every sense of the way. But part F is where things get ugly. In part F, if you drop the confidence, your interval is narrower, we actually like higher confidence. That's why this current problem here was at 99%, because it's a majorly important problem that affects public health. So they went for a high level confidence 99, And they don't care if their interval is wider. They just have to be punished by that while maintaining high confidence in the actual interval in the first place. Well, those are the kinds of constant questions, again, you'll see in my stats lab. Anything that talks about changing confidence level or changing sample size, you can come back to this note as a guide to see what they're really going for on those questions. What we'll do next on this set of notes is just take a look at a third example. Confidence intervals are kind of weird, so I felt like lots of examples was a good idea on these notes. And also, these are basically the last question on exam 3, so we're practically just reviewing in this sense. So let's take a look at a new context here. Example 3 says, the technology underlying hip replacements has changed as these operations have become more popular. It says here, over 250,000 in the United States in 2008 were done. Total hip replacement is like a crazy amount of torture, I'd have to imagine. So that's 250,000 people that went through a lot. And it's not always a good outcome. Sometimes it just fails. But the good news is that they say, starting in 2003, highly durable ceramic hips were marketed. That's kind of alarming. You wouldn't want a total hip replacement and be told it's not durable, but these ones were. So we have ceramic hips now. But it says, unfortunately, for too many patients, increased durability has been counterbalanced by an increased incidence of squeaking. And you can imagine that that's funny at first, right? Until your grandma just loses it after bending over to grab a can, and just that squeaking over and over again could drive you crazy. So this is actually a pretty serious problem. You could have everything go right, but now you make weird sounds every time you move your hip in a weird way. People investigated this. It says in May 11th of 2008, in New York Times, they reported that in one study, 143 individuals received ceramic hips between 2003 and 2005, and 10 of the hips developed squeaking. So these are 10 individuals where we don't even know what to do with them. This is a brand new problem. Let's say what we know so far, though. Has anyone spotted the sample size in this problem? Absolutely. The 143 individuals with ceramic hips. We'll just say 143 for short. So if we have 143 subjects, and we're being told 10 of the hips develop squeaking, that's the number of successes right here. So we'll say here, 10 successes. And we also said what a success is. The hip develops squeaking. Again, this is another one of those situations where it's a bad outcome, but it's the one that we're studying, so we call it a success. With all that in mind, we can now define the unknown parameter. When it says unknown parameter, in this context, categorical data, it's P. Actually, let me go this way. We'll say P equals the population proportion of all, and with whatever goes here, we're mentioning the population. So I guess that's a question in and of itself. Has anyone spotted what the population is in this problem? Exactly. Specifically between 2003, 2005, but we can let that part of the article carry our context and just mention the ceramic hips. So P is the population proportion of all people with ceramic hips. Right. I think on this one, I'm leaving that part off, but no harm putting it in as well. I'll let the context of this problem convey those hips specifically. So P is the population proportion of all people with ceramic hips. This is referring to the success. What would you all put on this last part?
Squeaks.
That squeaks, exactly. So all people that have hips that, you could say develop squeaking, but let's just say that squeaks. Again, it's kind of a fun problem until you can imagine this happening to you. After 12 years of squeaking, that would be just a little too much, I'd say, for just about anybody. You'd want to turn your hearing aids down or something like that to try to get some relief. Well, that's the hard part. When we go to give the confidence interval, we'll say the true proportion of these people with that have hips that squeak are from one percentage to another. And that's a pretty important figure, but here's our estimate already for what P is. We can calculate P hat. It's the sample proportion of successes. We just have to know when this comes up. We're being told calculate P hat. So let's write down the formula first. P hat is number of successes divided by sample size, which we just simply call n. So in this problem, it's going to be, we found 10 successes. It's being divided by, exactly. So now all that goes into the calculator. 10 over 143. We're being asked to round to 4 decimal places on this one. So we've got a 0.0699. Now imagine if we stopped right here. We would tell everybody, the whole world, that it's about 7% of the people with ceramic hips that will develop squeaking. If people took that information, they might not be too happy as years and years go by, because this could be way, way off. What we need is a way to say just how accurate that is. Even though it's true that P, that's the unknown, is approximately P hat, like we mentioned all along, that's a useless estimate until you can say the error in that estimate. In statistics, by error, we mean margin of error. You have to build out the entire confidence interval to give an actual honest and useful estimate. Because sure, it's about 7%, but it could be way lower, maybe around 2%, and also could be way higher, maybe around 15%. We don't know until we calculate. So let's go off to the next phase then. Next thing you'd want to calculate is standard error. And by the way, this last example is formatted pretty close to what a real exam question would look like, where the steps are really just broken down into components. And then when you're in part D, you're just putting everything together. So SE is our standard error. If you put P right here, you'd be putting P hat in this location. In chapter 14, mu goes here, and so Y bar goes in this location instead. But standard error P hat will be just another one of these computations, square root of, don't know why I left that in black. I think I wanted to keep that in green. Let's first write the formula. P hat, 1 minus P hat, divide by the sample size. So next on paper, we'd write in square root 0.0699, 1 minus 0.0699. So all I've done is plug in P hat into those 2 positions there and copied verbatim everything else. Then there's a division bar. Sample size we look up again as 143 and put inside there. Then just pick your favorite method of computing this and we'll have an answer. Let me clear this out. I'll go the order of operations way for folks that like that approach.
4.54, and then it has an E at the end of the day of 4.
Oh, that's interesting. Let me calculate that along with you and see what we get. So putting that in, I'm going to start with a 1 minus. So 1 minus 0.0699. We've got this then, 0.931. We'll multiply by 0.0699 again, times 0.0699. Now I'm up to that figure. Hit division, and we're dividing by the 143 you see here. Now it's down to this. I have the scientific notation you mentioned, E negative 4, but it's not our end answer yet. We still need the square root of it. So hit second, square root button. We need to put this number inside there, which seems kind of offensive, but there's 2 ways to do it. Either up arrow and hit enter, or if you hit second and the negative sign for the prior answer, that does it just as well. Either way we get it, we have 0.0213. So 0.0213. It's possible, by the way, if the sample size is really large, you might get an answer in scientific notation. If that happens, just write it down with as many zeros as you'd like, as you need to in that problem. So you'll have to undo that scientific notation. But any questions at all, folks, to this stage? Okay, so we're being asked now at this stage, are the conditions for the confidence interval met? It's kind of rude after we did most of the work getting towards the confidence interval, but let's take a break and just take a look into that information. So we have an issue from New York Times, reported 143 individuals, no information on how they got them. We just hope that this study did it right and it was a random sample. Let's start by saying on part one here, we do not know if the sample is random. In condition two, we're just quickly looking if the sample size is large enough. So we have to check if the number of successes is at least 10. And we are right at the benchmark of that. If it was 9 successes, that's enough for us to say we can't use this method any longer. Our interval wouldn't be as accurate as we need it to be. But this one right at the fence, it does pass. Let's write here, number of successes equals 10. This looks really weird, but let me write this down anyways. 10 is definitely greater than or equal to 10. Again, that's a weird statement, but the part in yellow is there because that's what we're checking no matter what the number to the left is. So because it's true, 10 is bigger than or equal to 10. It passes on that end. Next, we check the number of failures. Looking towards the sample size. Sorry, say again.
Right, it's 143 is greater than or equal to 10.
Well, we wouldn't use 143, it'd be 133.
Minus the 10. The 10 success.
Yeah. So this is the total sample size, but 10 of them were successes in our problem. That leaves 133 failures, or 133 people whose hips did not squeak.
So D is on our, if this were to be an exam and
Yeah.
for number 2, could we write down? Oh, I guess we would just be right 10 is greater than 10 because there's 10. Got it.
Yeah. And then just turning over to the failures, we'd say number of failures equals, we can take the sample size n minus the 10 from the line above. So it's 143 minus 10, and we get 133. Here's the other obviously true statement, but let's say it for the sake of the notes. That part's also greater than or equal to 10. We'll check there to convey we're happy with that. So we can now say the sample size is large enough. If this was a real exam problem, the major thing that I'd be looking for in your notes is not necessarily the greater than or equal to 10. If you left that off, I'd say that's okay. It's good to put in because it's a reminder. That's the benchmark you're trying to fulfill. But you would have to show this on paper. What I'm looking for is that you know the number of successes and you know the number of failures. As long as you state those two and then assert the sample size is large enough, you're in great shape. Well, we usually put in an extra statement under this and say, if the sample is random, then the conditions are met. But if in an exam setting, you just went up to the next problem, that's totally okay as well. I would say that this is the minimum amount of work you'd want to put down on paper when you're discussing the conditions. Well, any last questions, folks? Running through those conditions? Okay, well, we're almost there. For a 95% confidence interval, we're going to need a couple components. We need p-hat and standard error. So here's our temporary screenshots on those. Don't know why those always are so large as a screenshot. But the next thing we also want is, if we're at 95% confidence, from there, we get a Z star. It's a table lookup on the top of the notes like we mentioned before, but anyone happen to know what it is? Just by rote memorization, basically. 1.96, good call. One way you can think about it is, for 95% with the 68, 95, 99.7 rule, 95% of the area under the curve is within about 2 standard deviations. But if we use Z star 1.96, we're even more accurate. So that's the figure that we typically use. So let's see, we've got the confidence at 1.96. We have p hat, we have standard error. Next thing we write down is just the entire confidence interval formula. P hat plus or minus Z star times standard error, P hat. Forgot to color code these, but I guess that's what the highlighter's for. At this stage, we're just plugging in information. From P hat, that one came out as the 0.0699 down below on the next page. And subtract the Z star that we have at the very top of this part, 1.96. Now, final part for standard error, that's just turning into 0.0213. At this stage, we're done with that information there. We're ready to calculate the interval. But any questions at all, folks, getting to this stage? Okay, so here's our final answers on this. We have the parameter P in the middle, 2 inequality signs, and now we're just going to get the lower bound. Again, let me know if your numbers go a little bit weird, and we'll double check these in our calculators. In my lab, you definitely want to put the lower number first. I think that would potentially make us lose a question, which means you're using the negative sign first. So type in 0.0699 minus the 1.96. I'll go with parentheses this time. Close that parenthesis, open a new one to indicate multiplication by 0.0213. And this is what I have for the lower end. It's a point, let's see, 3 decimal places on this one for our final answer, 0.028. That look right to folks so far? Awesome, glad to hear that. So let's record 0.028. Now, doing it again is more as accurately as possible. Up arrow, hit enter, scoot the cursor over to here, and change it to plus, right ahead of the 1.96. And here's our upper end. To 3 decimal places, this one rounds up to 0.112. We did it, folks. That's our total confidence interval. It takes a lot of work to get to here in a statistics class. And the only last thing we have to do is give it a practical interpretation, mentioning the context. But the context is already being written out. We just say what P is once more. So let's start off by making our statements. First thing we have to say is the level of confidence. Let's begin with, we have 95% confidence that, now let's recall what P was. I could scroll up, but I think this one wasn't too bad. P is the true proportion I think I said population proportion the first time, but those are just stylistic choices. No harm either way. And I did say proportion, didn't I? Well, let's just go with it. It's a proportion now. We have 95% confidence that the true proportion of these ceramic hips that develop squeaking is between, again, I like percentages, but let's keep it as a proportion just to signify that's completely correct as well. It's between 0.028 and 0.112. If you like the percentages better, then you might have said IE between 2.8% and 11.2%. Notice there is a pretty big width between this, and the implications are pretty major too. If it's around this figure, that's great, only about 3%. That would say the ceramic kit was probably a great medical success, I'd say. But if it's over 10%, then maybe they should really look into that design. Maybe that's a problem where people might start getting sued, for example, in small claims courts, things like that. Doctors might be in a little bit of trouble there. Well, in either way, we at least have an accurate feeling of where the parameter P could be. If we simply stopped right here and said about 7%, wasn't the full story at all. It can range between 2.8 and 11.2%. So any figure in there is totally plausible. And what's even worse, that's just at 95% confidence. It's totally plausible that the true proportion P is even smaller than 2.8%, or that's bigger than 11.2%, for example. How do we be sure? Well, we can't. But one thing we could do is just repeat the entire study at the same sample size, getting more information, and compare the confidence intervals. Sometimes that's how statistics works, just repeating studies and doing what they call a meta-analysis. But for a very first study on this one, that's the best information we have, between 2.8% and 11.2%. Well, that's our entire unit on confidence intervals, folks. Any questions or comments about them so far? Okay, let's save this up. When we come back next class, we're changing gears in a pretty big way. It's still confidence intervals, but now we're taking a look at confidence intervals for means. And this is a good time to mention some interesting figures in statistics. These are just 2 pieces of optional reading, but these guys are major. Just like Isaac Newton is a big figure in physics, Ronald Fisher and William Seeley Gossett, the man behind the inverse T distribution, are 2 major figures in statistics, and they are recent from 1924. So this is pretty interesting background information to show what's going on in chapter 14. But any last questions at all, folks, before we call it a day officially? Okay, well, have a great one, folks. We'll take a look at chapter 14 and then review when we come back on Thursday.
Don't forget to vote tomorrow.